I'm very grateful to be here, and it was a pleasure to work with Dr. Hedengren. And it's been a pleasure to be here on campus at BYU. I graduated from the University of Utah, and I'm from Utah, so it's been really nice to get some exposure to BYU, and I must say I'm extremely impressed with the quality of the students and the openness and friendliness of all the faculty who have taken really good care of me. Very grateful to be here. My topic is smart energy storage. I'll explain what that means to you here shortly. So to introduce my topic, as motivation, I've shown you a plot of solar radiation. This is in units of watts per meter squared. This is measured from a building next door to mine in Austin, Texas on a July day. So everyone is really excited about solar energy and wind energy. People don't want to burn fossil fuels. They want to have this clean energy and sustainable energy, and the sun is a really important source of energy. And so my research is focused on taking something like this. You can see no one uses energy like this. It's intermittent. It's sporadically available. We can't control when the sun goes behind a cloud. So my research is really focused on integrating intermittent sources of energy like this into our existing infrastructure. So there's a lot that's great about fossil fuels, and I guess I can say this at BYU, I think the Lord has really blessed us with this great source of energy. That's where we have a 300-year supply of coal, and that's a really great blessing, but I do think there are a lot of opportunities to integrate technologies like this into our existing infrastructure. I mean, we have hundreds of trillions of dollars invested into fossil energy, and that's not something that's going to change anytime soon. So in order for us to ever actually achieve wide-scale adoption of intermittent renewable sources like this, we're going to have to find really smart ways to integrate these technologies into the system that we already have. So we're not only dealing with intermittency and this transient nature of energy when we're talking about renewables like solar and wind, so we also use energy intermittently. So these are real-time measured energy usage. This is for the state of Texas. So Texas likes to be kind of independent. We have our own electric grid that's pretty much independent of the rest of the country. So this is from ERCOT, which is the Electrical Reliability Council of Texas. So this is the entity that manages our electric grid. This is the amount of energy that we use on a July day. So you can see this fluctuates quite a bit. So we're going from 37 gigawatts of power generation and consumption all the way up to 66 gigawatts. So to give you a frame of reference, a gigawatt is approximately the power output of your standard coal-fired power plant. So we're talking about a lot of energy here, 66 coal-fired power plants to keep the state of Texas up and running. So in your design courses, you probably focus just on steady state. You assume that everything just happens. You have constant temperatures, you have constant pressures, you have constant flow rates. So particularly in energy, that's not the case at all. And what we have to do actually is we have to be switching on and off power plants at certain times. So this right here is called the peak demand. So you don't want to build a really expensive nuclear power plant or a really expensive coal power plant that's only going to run for a few hours a day in order to meet that peak demand. So what a lot of utilities will do is build really cheap gas-fired power plants that are designed to be just that cheap. And because they're really low on capital costs, they're really inefficient. That power on an operational basis is actually more expensive, and they'll pass those costs on to, so the generators will pass those costs on to your utilities. You as consumers are probably shielded from a lot of the price fluctuations that may happen, but these issues are real, and your utility is going to absorb those costs, and they're going to annualize it and pass it on to you. So these issues do affect you, even though your rate that you pay for electricity doesn't change from one hour to another. It may in the near future. So if we were to come up with some way to deal with these different issues, so intermittent nature of renewable sources of energy and this transient demand, then we'll be in a lot better shape, and we'll be able to integrate some of these transient sources much better. So this is the overview of my presentation. So I've already addressed this issue of intermittency. So there are two ways that we're going to overcome intermittency of power. So the first one is something called a smart grid. So your electric grid has been designed around this concept of burning fossil fuels whenever we need them. And that's what makes fossil fuels so great, is that when you need energy, you burn that fuel and it's there whenever you need it. But with this new paradigm of a smart grid where we're trying to integrate intermittent sources of energy, we're going to have to change the way we operate our electric system pretty substantially. So the smart grid is kind of a buzzword that's been thrown around, and I'll hopefully give you some kind of, there's not really a formal definition, but I'll try and help you understand what it implies. So the other key pillar to overcoming intermittency is, okay, well, first of all, the smart grid is dealing with generation, distribution, and consumption, trying to make all those parts of the system interact harmoniously. The other key pillar to making the system work is energy storage. So you saw that solar power plot. Well, if, let's say at times when there's a lot of extra solar power available, if we could store that energy, then when the sun goes behind a cloud, now we have this extra energy that we can tap into, then we can level out that curve, so it's something that's what's called dispatchable power. So dispatchable means it's available when you need it. So my research is focused on taking the concept of a smart grid. So a lot of research is focused on just getting this stuff to work, just getting these things to operate. What if you add in a lot of solar? What kind of electrical system do you need to supply that solar? So just a lot of research are trying just to make things operate without shutting off the power to entire cities at a time. So storage helps a lot with that. My research, though, is taking this to another level where we're taking that storage, we're trying to see how that integrates with our system. So how does storage interact with our generators and our distribution systems and our consumers? And how can we use that storage so that we're not just making our system operational, but we're making our system optimal? So this is the term I came up with for my presentation. Smart energy storage is integrating storage into this really complex energy system, and then using tools that are synonymous with smart operation to make the whole system behave optimally, so that we're trying to minimize our energy consumption, we're trying to maximize the benefit to consumers like you and me. So I'm going to talk about each of these things. I'm going to talk about some of the tools that we use to make this whole system happen. So some of the key pieces of my research are dynamic simulation and optimization. I'm going to apply this concept to two different systems. So first is a distributed energy system, and the second is a solar energy system. So I have this kind of central idea, and in my research I've applied this to these two different systems. The problems that I'm solving are actually quite different. And finally, in line with our session about graduate school and about the NSF, I will share a few of my thoughts about graduate research opportunities and applying for NSF funding. So the next thing I'm going to talk about is the smart grid and what that means. So here's a really scaled down version of what the smart grid means. So if here's your building. We have all these different systems that are trying to interact together and do so harmoniously. Where previously you could imagine a power plant and power lines and then a building. Now we're trying to integrate wind, we're trying to integrate photovoltaics. There's starting to be plug-in electric vehicles, which you plug in one of those and suddenly the electricity consumption at your home shoots through the roof. So how is the grid, the electric grid, going to handle all these things? Energy storage is really important, and a really key piece of this research is the dynamic systems and control. So dynamic systems and control is a really key part of this research. And when I took process control, I think, so Derek Harris was in my class. Did you like that class, Derek?
Yeah, I did.
Okay, you and I were maybe the only ones. So I really loved process control. My passion was to take a system, to put some math that describes how it works, and then use that math to figure out how to make the system behave better. I was really interested in energy, so I found this project that allowed me to integrate those two passions of mine into a single project. So the dynamic systems and control here you can see is critical. We have all kinds of crazy things happening. We have solar that may be fluctuating. We have wind that will be fluctuating. We may plug in hybrid cars. So there's a lot of research going into making this system work so that we don't have outages, and so that everyone stays happy and we can still get wide-scale adoption of some renewable technologies, which are very low right now. All right, so now I'm going to talk about energy storage and what that means. Okay, so you saw that grid where the power is fluctuating in Texas by like 30 gigawatts. So that's a lot of energy to have to displace or to try and store. So we wanted to avoid using those peaking power plants, those inefficient power plants. We need some serious long-term energy storage. So it's got to be large scale, and it's got to be really inexpensive. So essentially we need some really heavy lifters. So here's a heavy lifter. He says, I lift things up and put them down. You may have seen this commercial. That's all he can say. That's all he knows how to say. But he's powerful. He's strong. He can do a lot. So the first energy storage technology that probably comes to your mind is batteries. So I actually brought with me a couple of energy storage devices. So I brought a laptop battery. So who has purchased one of these recently? Or who has priced one out? Can you give me a price, approximate price for a battery?
Amazon, $22.
$22, man. Okay. That's a good deal, then. So I recently got a 9-cell battery that lasts about 5 hours, and that cost my research advisor $150. So I would say, if I hadn't asked you that question, I would have said $100 for a laptop battery. So I have another really high-tech energy storage device. A coffee thermos, a hot chocolate thermos. So these two devices hold approximately the same amount of energy. If we could heat up some water close to boiling, we get about a 70-degree temperature difference. Do the calculations. So this battery holds 56 watt hours. You can do the calculation here. They hold approximately the same amount of energy. Any guesses as to how much I paid for this? So if I turn it around, got it at the career fair for free. So you can see, so batteries are obviously, they have some advantages. They're really versatile. So storing electrical energy is really valuable, and batteries won't be replaced, and I'm not trying to imply that they will. Batteries are extremely versatile. They store energy in a very high quality form. Again, we talked about cost, where battery technologies, so you could scale this up and you're going to get economies of scale where this will become a lot cheaper. Lithium-ion batteries, probably not the technology of choice for wide-scale grid storage. But you can see, you can get the point here. There's a lot cheaper ways to store energy. It may not be quite as valuable. And so batteries are really good for maybe short-term storage, where if there's a sudden outage, you could turn on a battery to help smooth out any fluctuations while you're ramping up a generator to help meet the demand. So what we're going for, and my topic is thermal energy storage. So that's storing energy as heat or as cooling. So it may kind of seem like the brute force technology, but it does have the potential to be a heavy lifter, like we talked about. In Texas, so at the University of Texas, our campus, about 1/3 of our total energy costs over the period of a year, it comes from air conditioning our buildings. So 1/3 of the energy. So even though this isn't quite the really high quality energy that you get by storing electrons directly, you can displace a lot of your energy production by using a thermal storage system. So it's really inexpensive. And instead of lifting things up and cooling them down, our heavy lifters, we heat things up and we cool them down. So thermal energy storage, you can do this with just about anything. So let's say that the costs of that fluctuating energy demand are passed on to you, where now you have to pay a lot more. Let's say you have to pay triple the amount in your apartment during the hours of 2 to 6 p.m. when it's summer and everyone's got their air conditioners fired up. So if you were smart, one thing you could do was, electricity is going to be really expensive between 2 and 6 p.m. You could really crank up your AC between 12 and 2 p.m., maybe get it down 10 degrees lower than you normally would. Then during 2 and 6 p.m., you don't have to run the air conditioning as much, and you avoid some of those costs. So energy storage is just as simple as that. So in that case, you're cooling down the air in your home, you're cooling down the walls, you're cooling down the furniture. So you're heating things up and cooling them down. It's a pretty simple concept, and the title of my talk is Smart Energy Storage. And this may not sound like a super smart technology. It sounds like kind of a brute force technology. So what we're really aiming for is something that can be both powerful and smart. So I obtained this picture of Dr. Hedengren before coming to BYU, before he had to start living the honor code. Okay, so this is actually not Dr. Hedengren. Does anyone happen to recognize this guy? I wouldn't have. Okay, so this guy, his name is Dolph Lundgren. Do you recognize him now?
Uh-huh.
He played Ivan Drago in Rocky IV. Big Russian dude. Okay, so this This is what we're going for, and I'll tell you why. So this guy, obviously, he's got the power. He's a brute. He's a chemical engineer. I'm serious. So he got a bachelor's degree in chemical engineering. He went to the University of Sydney in Australia, graduated at the top of his class with his master's degree. He was awarded a Fulbright scholarship to attend MIT. So this is a very smart guy. So this is an indirect way of saying that powerful can be smart too. Just because something is powerful, it doesn't mean it just we have to resort to brute force methods. All right, so that brings me to the next part of the topic, which is smart energy storage. So how do we take that brute and how do we make him smart? So it's going to involve optimization, and it's going to involve integrating all the other components of our system. So in itself, thermal energy storage is really simple. When you're camping, has anyone ever taken a rock and you heat it up by the campfire and then stick it in your sleeping bag or something? That's thermal energy storage. So it can be smart, but we're going to have to start considering the other parts of the system so we can use the storage to make all the parts of the system be synergistic. All right, so first of all, I'm going to give you this crash course in optimization, but I'm going to relate it to some of the topics of interest. So first of all, when you're doing optimization of a system, you need to have a model of a system. So I've generated this surface plot. This is totally made up, but this will illustrate some of the points. So let's say we have two different generators. So P1 is the power that you generate from turbine 1. P2 is the power that you generate from turbine 2. And then these level curves, we call them in optimization. So every curve represents an efficiency. So along this curve, if we operate 100% P1 here, and we operate it at this power, then we're going to be generating electricity at 25%. Or we could come around this curve and switch completely to P2 and be operating it at some level. So this is think of this as like a topographical map where this is a mountain that we're trying to climb. So this is the peak of the mountain. This is the peak efficiency that we're trying to obtain right here. So you can see there's a difference in the efficiencies of these two turbines, where P1 is much more efficient. Let's think of P2 as a peaking power plant, an inefficient one. We don't want to use it as much. So if we're trying to maximize, we take our model. So this is the math that describes what our efficiency will be using some combination of those two generators. So first we need an objective function. So an objective function is the thing that you're trying to maximize or minimize using that math. So let's say we're trying to maximize efficiency. We need to figure out what our decision variables are. What are the things that we actually have power to change? So those are also known as degrees of freedom, which is probably a term that's familiar to most of you. If you have a system with 6 equations and 6 unknowns, then you have 0 degrees of freedom. You get your answer, and that's the only answer you can get. But if you have a system that only has 5 equations and 6 unknowns, now you have 1 degree of freedom, so you can use optimization to take advantage of that degree of freedom. You may want to maximize power or something like that by changing that one free variable that you have. So in our system, if we're trying to maximize efficiency, and that's all we're worried about, we have 2 degrees of freedom, so we have P1 and P2. So we're going to look for our optimal solution, which you can see it right here from this graph is right about here, so just over 45% efficiency. So what's the point of just trying to maximize efficiency? We really have to generate power and deliver it somewhere, right? So we have to deal with what are called constraints. So those are more equations that we add into our system. And so in this case, we want a constraint. We have some total power demand that we're trying to meet, which I'm calling P total. And we want P1 plus P2 to equal our demand. So that adds one more equation into the mix, so that reduces our degrees of freedom down to 1. So now we can only move P1 or P2 independently, but not both. So if we took our 2D plot and graphed, okay, so let's say we're trying to meet some power. We're going to look at our max demand and our min demand. So our minimum demand, we're trying to meet our load at the trough. Then that's where our constraint is. That's our P total. So we need P1 plus P2 to be equal to our P total. So you can see on this line, so now we're constrained by this line. We need to find the point on this line that maximizes our efficiency, but we're still generating that total power. So that point is here. So it's pretty easy. We don't want to use this inefficient peaking plant. We want to use the efficient one. So let's say at our maximum load here, we have this higher total load. So now our optimal solution is right here. So we have to use our peaking power plant if we want to get optimal efficiency here. So we have to use a combination of P1 and P2. So that's optimization in a nutshell. It becomes a lot more complex than that. So once you get beyond 2 degrees of freedom, you can no longer plot them like this and just look at the graph and say that's where the optimum is. You got to get to a lot more sophisticated tools where you may be looking at hundreds or thousands of decision variables, and you can't visualize that in your head or on paper. You have to go into the math and use optimization algorithms to find where the optimum is. Okay, so this is a pretty simple system. Any questions right here?
P2.
Okay.
P1, P2.
Okay, so P1 is the total power that you're generating from a power plant, a turbine. P2 is a different power plant. So you have 2 power plants. Combined, they have to meet some total power demand. And you can have, so you could say, I want 1 megawatt. If your total demand is 2 megawatts, you could say I want 1 megawatt from P1 and 1 megawatt from P2. But there are a lot of different combinations that you can have. So you want to find the combination of P1 and P2 that gives you the optimal efficiency. Does that answer your question? Okay. All right, so we've looked at this fairly simple system. Now let's add energy storage into the mix. So let's say that you can see we're not really operating as efficiently as we could here, and we want to increase our efficiency. Well, what if we produce extra power here so that we can run that turbine more efficiently? If we're trying to produce power up to that line, we can shift this total power curve. So now we're generating a little bit more power. Now our optimal solution becomes here. So we shift that load, we shift P total. So now we generate a little bit of extra power here. Well, we can store that energy if we have an appropriate energy storage system. So now we produce that power much more efficiently. Well, now, why would we want to produce extra power? Well, if we have that power stored, then we can use that power later, and we can reduce our peak demand. So now, if we stored energy here, we could extract that energy here. That lets us not have to rely on P2 anymore. We can meet that entirely with P1. So now, here at our max time of the day, we start using our system more efficiently because we're generating less power. We don't have to use that peaking power plant. And in this made-up example, we actually get better efficiency here when we're storing energy. We're producing more and we're consuming more fuel, but we're getting more energy out of it. So you can see if we use energy storage, now before we had 1 degree of freedom, so we had 1 decision variable. Now with energy storage, we're going to be looking at, so I've chosen 2 points in time here, but time is continuous. You could produce at this power rate, which would be measured in watts. You could produce that power rate for 1 second, or you could produce that power rate for 10 seconds or 100 seconds or whatever. So really, when you start to look at storing energy, then you have to consider the dynamics of this process, what's happening in time. So now we can use energy storage. You've seen how we can improve the efficiency of our system because now we have more degrees of freedom. So now we have this whole range where we can store power or extract power. So that's a really good thing. Storage gives our system flexibility. It gives our system a lot more degrees of freedom, and we can use optimization to harness those degrees of freedom and to exploit them so that we get optimal performance. But now we're not looking at a steady state problem anymore. We're looking at a dynamic problem where we're trying to minimize our total fuel consumption, for example, over some time horizon. So now our degrees of freedom become infinite because we're making that decision every second or every nanosecond. We have to decide what we're doing. So now we have a lot of flexibility in our system, but we also have a really, really difficult problem to solve with an infinite number of degrees of freedom. So realistically, we would discretize our system. So we would say, okay, well, I'm not going to make a decision every nanosecond. I'm going to make a decision maybe every 5 minutes. So we discretize our system, we break up the time into chunks, and we try and make those decisions for every time interval. So I mentioned that it gives us flexibility, but that flexibility is a two-edged sword. It can make our system run a lot more optimally, but it also makes the problem a lot tougher to solve. So this is what's known as the curse of dimensionality. This is a quote from Richard Bellman, who is the father of an optimization technique called dynamic programming. So the more dimensions you add to your problem, it gets exponentially harder to solve. It takes a lot more computational speed. And there's also some other really negative side effects of dimensionality in these problems that we solve. All right, so I've explained how you can make energy storage smarter. So we don't want to just be using the brute force method where we just arbitrarily store energy and then extract it. We want to take advantage of those degrees of freedom. So I've applied this methodology to a couple of different systems, and this generates problems that actually become quite different in nature. I mean, by nature, the problems are very different, and some are easier to solve, some are harder to solve. So the first system we're going to look at is a distributed energy system. So I do simulation and computation stuff, but I've discovered my new laboratory. So this is my laboratory. It has a population of about 70,000 people. This is the University of Texas campus. And what's really cool about this system that we're working with is it's essentially an energy island. So we are completely energy independent, except that we import natural gas and we import water. So we have a power plant on campus, which we use to produce power. We use the waste heat from that power generation to produce steam. We send that out to heat the buildings on campus, to provide process steam for the labs. So it's a really fascinating system to apply some of these ideas, because it's essentially a closed system where we have the city at our disposal and can study how. So we have buildings. So buildings are actually a big part of our energy consumption. So according to the DOE, about 40% of energy in the United States is consumed in buildings, just office buildings like this one. So we have all these different components of our system. We have buildings, we have gas turbines, we have steam turbines, we have boilers. We have recently installed, so that concept is known as cogeneration, where you generate electricity with a gas turbine or a steam turbine. You use the waste heat to power, use the waste heat for something else. So you guys are pretty familiar with heat integration, where you take heat from one process and deliver it to another process. We do that here. So we have the capacity to produce 130 megawatts of power. So not quite a coal-fired power plant, but we have 2 gas turbines and we have 2 steam turbines. We use one combination gas and steam turbine for wintertime, and then another set for summertime. So we don't actually have 130 megawatts of energy demand. We probably get up to about 60 is our peak, but we have the capacity to do a lot more. So hence the title, Everything is Bigger in Texas. So all these energy sources are delivered on different networks. So now we're even getting into some of the distribution of energy. So we have to produce electricity, we have to produce heat and cooling, and we have to distribute that out to essentially the city. We recently installed a thermal energy storage tank, which is why I was predominantly interested in this project, where we have this big tank. It holds 4 million gallons of water. And we can now, I told you that a third of our energy consumption is cooling. Now we can shift that cooling to nighttime when we're not dealing with the peak, and that can become a lot more efficient for us. So that's 138 megawatt hours, that's thermal megawatt hours. So if you divide it by the coefficient of performance of your chillers, then you get 30 megawatt hours of electrical storage, essentially, so even though this doesn't store electrons directly, because cooling is such a big part of our demand, if you shift that cooling, you're essentially shifting electricity. All right, so here's our campus in a cartoony diagram form. So we have our combined heat and power station. We have these distribution networks, electrical, cooling, and heating. We have this thermal energy storage tank. And we've actually started working with the utility on campus, so I'm actually employed part-time by the utility. I initially proposed this project for my dissertation proposal. This is what I wanted to work on, was this power plant project. And I realized that this was an enormous project. It didn't take me long to realize that. There's a lot of different components. I'm certainly not a world-leading expert in chillers or in gas turbines, but there were other researchers around that were. So I proposed this project. UT was really excited about it. We're going to be doing dynamic optimization of our whole energy system using that storage. So the projected savings are about $300,000 a year for the school, so they have become really interested in it too. So because of all those different components of the system, we have a lot of work to do to try and figure everything out. So before I showed you that optimization example, where we're looking just at electricity generation, this problem becomes a lot more complicated because now we're dealing with multiple loads. We have a heating load to follow, we have a cooling load to follow, and we have an electrical load to follow. So we have to meet all these constraints for our system. It's a really highly coupled system, so here's what a CHP plant looks like. You feed fuel to your turbine, you take that waste heat, and then you use that to generate steam. So let's say we're rolling along, people start to show up on campus, and our electricity demands start to go up. Well, now we have to ramp up our gas turbine, so that means suddenly we're going to be generating more heat, but we may not need all that heat. So it's a really complex problem, and there's a lot to it. The energy storage here becomes critical because we can use that flexibility provided by storage to make the system perform optimally. So this does require having some foresight as to what your demands are going to be. So we are now forecasting what all these energy loads are going to be 24 to 48 hours in advance. So we do that using a model. So there's not really, it would be really tough to come up with for a whole campus how much electricity you're going to use using like physics or chemistry. So we have an empirical model. So it's essentially, so in Excel you've done like a polynomial curve fit. That's an empirical model. You stick your data points on there. You tell Excel, find the best fit to that data, and it gives you some equation. So we're using what's called an artificial neural network, which is an empirical model like that. It doesn't have a lot of physical meaning, but it's got as many fitting coefficients as you want. So it's really good at handling stuff like this, where there's not a real strong connection between your inputs and your outputs. It'll come up with some math, even though it may not be physically meaningful. It'll come up with some math to figure that out. So the inputs to this model are the weather. There's a lot of work that's gone into weather forecasting, so we're taking advantage of that. What's the weather going to be like? What's our occupancy going to be like? So occupancy, well, first of all, weather inputs would be temperature, humidity. Those are the two most important factors going into how much energy we're using. Occupancy is important because, so this would be like, what hour of the day is it? Is it a school day or is it a holiday? So occupancy variables are important. And then another thing that really makes this doable is, so here we're looking at, okay, we're using our model to say, we have a weather forecast for time I plus 1. So we have some kind of idea what the weather's going to look like an hour from now. And we can use that weather to predict what our load is going to be an hour from now. We also have measurements from the past. So we know what our load is now. We can use that load to predict what it's going to be an hour from now. So this model essentially lets us predict one time step ahead. And if we can add some what's called recurrency to that system, so we can measure what that load is, feed that back into the model. Now we have this recurrent model where as long as we have weather forecasts and some idea about occupancy going off 24 to 48 hours in the future, which you can go on weather.com and find a weather forecast. So we have that information. Now we can use this recurrent model. So first we're going to predict 1 hour ahead. Then our model is going to output that and say, okay, 2 hours ahead, 3 hours ahead, and we can do this. And it turns out that this actually ends up being fairly accurate. So we have this way to predict what our loads are going to be. So now we can add in storage to the mix, and we can figure out what we're going to do over this 24-hour period with our energy so that some objective is minimized. So our objective is to minimize the fuel consumption by our campus. I told you we only import natural gas, so that's really the only thing we need to worry about. So here's some of the results from that system. So this is just looking at the cooling system for now. So we apply this system. Now we're looking at which chillers to run and when to charge the system. So we have chillers that operate at different efficiencies. So what this does is, so optimization, if you're disregarding storage, you can use optimization to say, which chillers do I use and how much load do I put on every chiller? You can solve that problem really easily. So now what storage does is it says, how much load do I want to put on the total system? And storage gives you the ability to shift a lot of that load. So we're looking at this day. This is a 24-hour period. So you can see our wet bulb temperature, which kind of captures temperature and humidity into one variable. So our wet bulb temperature increases like this. This is what our demand is going to do for the next 24 hours. So if we take that, we can run our dynamic optimization, figure out how to use the storage optimally. So we get a 9.4% energy savings because now we're not just shifting to our most efficient chillers, we can also shift a lot of our demand to the most efficient times. So we're just minimizing energy here of our chiller system. And those chillers, they operate a lot more efficiently at the lower wet bulb temperatures. So this is, think of Carnot efficiency. Your thermal cycle is a lot better if you're rejecting heat at a lower temperature. So our chillers operate more efficiently here, so we can shift a lot of our load to those early hours, store that energy, then later in the day when we have peak cooling here, now we can harness all that extra energy. So that gives us, okay, so I applied a time of use pricing rate. So we're only part of the way into this problem right now. So I said if our energy was twice as expensive between the hours of 12 to 8, Then we resolve this problem, now trying to minimize cost. So we get a 17.4% cost savings. So what we're trying to do now is to look at meeting all those different loads and analyze the effect of switching on and off these chillers onto the rest of the plant. And one thing, I definitely will not get to this in my PhD, but if you can imagine having this enormous model of an entire college campus with 70,000 people, it's going to be really hard to get an accurate model. That's taking us a lot of man hours to get an accurate model. But think about your system. Your chillers are going to wear out. Your turbines may change performance. There may be maintenance events that come. There may be new buildings that are built, so your demands change, so your forecasting model has to change. So if you wanted to implement this system in real time, you'd have to have some smart way to update your model. So Dr. Hedengren does some work in what's called moving horizon estimation, where you have parameters in your model and you use past data to figure out what the value of those parameters should be. So I want to apply some kind of technique like that so that the system adapts in real time, so that the models learn. But definitely not within the next year. All right, so this is the collaboration that we've developed. So I initially proposed this as part of my dissertation, and I certainly saw the value in making this a collaborative effort. So we have a lot of different students. I know this diagram may be a little overwhelming, but don't worry too much about it. So here on this level are all the models that we have to develop. So we have boilers, gas and steam turbines, heat recovery steam generators, we have chillers, thermal energy storage in buildings, we have our forecasts. So the idea here is that all of us who are working on different kinds of systems, we may have interest in parts of these models. So we can generate these models together, and then we can all use these models for different things. So when you do PhD research, you have to have some original research. So each of us still has our original piece of research, but we're pooling our knowledge on all the models so we can all use them for different things. So my topic is energy storage, energy system optimization. We have Jose here at BYU. This slide is a little bit old, so I have him for boiler model predictive control, as this topic has changed a little bit since then. But we found a way to get all these different researchers, and the really cool thing that happened here was all these, so you're a graduate student, you're getting paid by someone, you have some funding source. So we got all the funding sources to be really interested in this project because we have access to this really cool energy system. So we have Jong, who's working with ChemStation. That you guys use ChemCAD at BYU, right? Do they use ChemCAD here?
Yeah.
Okay. So ChemStation makes ChemCAD. So Jong is figuring out how to integrate combined heat and power into their simulation software. Akshay is really interested in the forecasting stuff. Wes, who's a former BYU student, he's a lot more on the smart grid side. Building, so this is building model predictive control. We have another student doing that. We even have Texas Instruments that makes semiconductors interested in this project because they have thermal storage. All right, well, I will skip the solar thermal part of this project. So we applied this to a solar thermal system. So this is basically the same kind of concept, but we're applying it to a solar thermal system. I have 3 minutes left. So basically, I'll give you a really quick synopsis of this. So this was our brute force study where we modeled the system and we figured out how storage changes how the system operates. So here's our available solar energy. This is without storage on the left. Here's the solar energy that we actually deliver to our system. And if we're trying to meet some constant load, we have to change this fossil energy. So we have to be, first, you're not going to actually do this. You can't, no one's going to want energy like this. And you don't want to be ramping up your fossil steam generator like that. So energy storage lets us operate things smoothly. So we add an energy storage, now we have this buffer tank that we can draw energy when we need it. So I've taken that, so that's the brute force energy storage. If we add in dynamic optimization, where before we were trying to control to a constant power output and we were trying to control the constant temperatures, well, if we open up more degrees of freedom, where now we get optimal temperature heat collection, we give our system the opportunity to bypass storage. We solve this dynamic optimization problem over a 24-hour window. We take our system from being simply operational to being optimal. So we do this. So now if we know that we have some backup source of fossil power, we say, okay, maybe if the sun is behind a cloud here in the early parts of the day, we generate only a portion of our energy from solar, and we make up for it with fossil or some supplemental source of power. So that lets us run a lot more efficiently. So on a day when there's a lot of cloud cover, so normally these solar systems require you to get to really high temperatures, which is really hard to do when you have clouds passing by all the time. So if it's cloudy and we know it's going to be cloudy, we can store energy at lower temperatures, and we can only supply a portion of our energy via solar, make up for the rest of it with fossil, and we improve our system efficiency from 52% to 85.4%. I'll skip this one. So essentially what this could do, where this concentrated solar power is really only viable, and it's heavily subsidized right now, even down here, but it's really only viable in the southwestern US where you get a lot of solar energy. You can expect a lot of days with a lot of sunlight. But if we can take advantage of that lower quality solar heat, then we can expand that region a little bit further at least, so that we're sure that BYU is included in there. All right, and I will leave the graduate research opportunities. We talked about this a little bit earlier. I'll skip through this stuff. And I will open it up to questions now. I have one more conclusion slide after this, so I'll just ask for 1 more minute after the questions to finish up.
Okay, so let me open it up to questions then for Kody. Any questions, Mark?
So what temperature do you keep your thermal storage tank at, or how much does it fluctuate, and at what point does it get too hot or too cold to be a viable storage?
Okay, so great question. We're dealing with the 2 different systems. So the distributed energy system, we're storing chilled water.
Right.
So you're going to take that at so it's going to come into the tank at roughly 15 degrees Celsius, and you're going to store it at about 4 degrees Celsius. There's some interesting ways that they store it that I didn't have time to cover, but you don't want to get it to freezing.
Right.
So the solar system, but there's actually another form of thermal energy storage where we actually do make ice, but our system isn't designed for that. So there's all kinds of technologies out there. The solar system, our heat transfer fluid, is some kind of synthetic oil, which is only going to be stable up to about 400 degrees Celsius. There are other forms where we're trying to get to higher temperatures. They would store that in a molten salt. So it's something that's going to be solid up to like 260 degrees Celsius. Then it'll become liquid up to 500 or 600 degrees Celsius. So it's a pretty hot topic, getting materials that will store heat at a higher temperature, because then your Carnot efficiency improves in your power plant if you can store higher temperature energy.
Great. Okay.
So you call that long-term storage. How long will you be able to store and hang on to that before you start having significant losses?
Great question. So these tanks are really heavily insulated, as you can imagine. Our system at UT, so they actually don't have an operations strategy right now. And so just to keep the pumps working and make sure everything still works fine, they charge the tank on Sunday evening and they discharge it on Thursday or Friday. And it only loses about 1 degree Celsius in 4 days, 4 or 5 days. Yes?
So my boss made me read an interesting critical review by MIT about the water and energy nexus. What he calls it basically, we need energy to produce water, we need water to come up with the energy. And one of the things he had, besides a cool or a power and heating plant, he was talking about using basically a power plant and hooking that up to a water generation and purification plants.
Yeah.
I mean, obviously, the University of Texas doesn't have this at their Austin campus, but is that a significant portion of the U.S. potential for having some sort of demand that you can control and manipulate?
Yeah, there's actually, so you could search for solar desalination of water. So that is a pretty hot topic, and it's pretty easy to get water and salt separated. And the slide that I skipped is not just looking at power generation via solar, but opening this up to a lot of different technologies where you can integrate solar heat into your chemical plant or a desalination plant. So I want to looking at other degrees of freedom where you can deliver heat. So in a typical power plant, you'll have different temperature heat sinks. You'll have a superheater, you'll have a steam generator, a preheater. You may have a reheater, which will help you improve your turbine efficiency. So you have these different heat sinks. You also have different temperature heat sinks in a chemical plant. So I want to look at being able to route that energy to different heat sinks. So if it's a little bit cloudy, for example, you could bypass your superheater because you can't reach those temperatures and go directly to your steam generator or even to your preheater if you're really not getting very much energy. So it's kind of a tangent, but yes, solar desalination is a process where we're actually applying some of these concepts.
Okay, so you have one more slide then?
Yeah.
Okay.
All right. So just to conclude, so if we want to get widespread adoption of renewable energies, we're going to have to figure out how to integrate these into our actual energy infrastructure. We need to be realistic. So that's going to require smart operation, and it's going to require energy storage. So thermal energy storage is a low cost but can be a really high impact technology that integrates really well into solar thermal and district energy systems, as I showed you. If we have storage and optimization, we have all these new degrees of freedom that we can take advantage of. They become difficult problems to solve, but we're finding ways to solve them, and we're finding some pretty significant energy savings. So we've identified some really big problems. This is a collaborative multi-year effort. I'm hoping to extend this beyond my PhD. I think there are some good funding opportunities out there. And even though these are really challenging, the optimist sees the opportunity in every difficulty. So that's what research is. When you get stuck at some really tough problem, that's when you should be really excited, because that's the kind of problem that the world needs you to solve. If it had already been solved, if there was some easy answer, you wouldn't be employed as a graduate student. Thank you.